Okay, so we continue with the discussion of the acid-base chemistry of alcohols and phenols. So here we have a couple of cases. We have the structure of the methoxide. So that is the conjugate base of methanol, CH3OH. So if methanol gives away a proton, it will become methoxide. You may want to put the lone pairs of electrons there. And then same thing we can do with terbudoxide. So you have three methyl groups attached to the carbon atom that is bearing the OH. So here also I will put my lone pairs there. And so that is the conjugate base. So and then due to the size of the alkyl groups, here you can see that it's more difficult to solvate the O minus of the alcohol in the terbudoxide. In the methoxide, it's easier because, well, the alkyl group is relatively small. So and that's why, because you have better solubility and better solvation of the methoxide, that is the reason why the pKa value is slightly lower than the pKa value of the terbudoxide. Also, we have some inductive effect. The fact that alkyl groups, they are electron donors, and here we have just three hydrogen atoms attached to the carbon atom, right? So three hydrogen atoms. So the electron donation power is not so high. So the electron density of the carbon atom that is attached to the oxygen is not as high as it is in the case of the terbudoxide. In the case of the terbudoxide, we have three methyl groups, and all of them, they are electron donors. That's why the electron density will be higher. And that's why that will destabilize the level of energy of the terbudoxide. So all the time, we need to consider two factors for having an estimate on the stability of the conjugate base. One of them is the inductive effect, and the other one is the resonance effect. Inductive effect, it decreases very rapidly with the distance. And so if you have electronegative elements close by to the reaction center, there is a great influence. For instance, here, the pKa value for terbutanol, so terbutanol is this. So we have three methyl groups and an OH, and that is terbutanol. So the pKa value for terbutanol is 18. But the pKa value for a similar system with fluorines, as we have on the left here, and so you have CF3 parenthesis 3COH, so that is the trifluoro system. So there it decreases to 5.4. Why? Because you have each one of these trifluoromethyl groups, they are pulling electrons very strongly. So that will decrease the electron density of the central carbon atom, and that will be beneficial in order to stabilize a negative charge. So here it works very nicely because the trifluoromethyl groups are right next to the carbon atom that is bearing the OH, right? But if the group was farther away, let's say if you have something like this, you have an alcohol here, and if I have my three CF3 groups farther away like this, so in that case, I could bet that the pKa value of this system, it will be very similar to the pKa value of methanol So it will be around 16. So there will be not much of effect felt by the OH due to the presence of the CF3 groups, because those are too far away. Same thing will be true, and we will see that in the future, in the next semester, when we talk about the effect of electronegative elements on carboxylic acids. We will see, for instance, here we have the 2-bromopentanoic acid is substantially more acidic than acetic acid. Acetic acid, the pKa value is around 4.8. If you have a bromine now that is next door there, just in the next carbon, there is a very, very important decrease in the pKa value. But if the bromine is farther away, like in the case of the 5-bromopentanoic acid, there you can see that the decrease is just from 4.8 to 4.7. And so it's very, very little. So that is a very important thing. The effect due to inductive effect, it dies very quickly with distance. Then now we have the question, how can we prepare alkoxides? Well, there are several ways in which you can prepare alkoxides. One way is by reaction with an alkaline metal. So you can use potassium or you can use sodium. Now, those reactions are rather violent, so you need to be careful when performing that in real life. What is happening in this reaction in terms of oxidation reduction? Well, so we have potassium 0 is getting oxidized to potassium +1, right? So who is getting reduced? The one that is getting reduced is hydrogen. And so we are having hydrogen +1 that is getting reduced to hydrogen 0, right? So that is interesting. This is a redox reaction. So, and you should be able to write down a mechanism for this reaction. I will give you a little hint. So you will have OH. You will have two turbidoxides that they are reacting, right? So then you can have two of these hydrogens that they will form H2. And then you will have a potassium that will donate one electron to the alkoxides that you are getting there. And then you will end up with, at the very, very end, you will end up having two molecules of turbidoxide and two potassium plus, right? Potassium plus. The other way in which you can produce the alkoxide is by reaction of methanol with sodium hydride. Remember, sodium hydride, what is that? It is H minus and sodium plus. So what is happening here? So the H minus is reacting with methanol to produce hydrogen, and then you are producing the methoxide. And then yet another way, it will be using sodium amide. You know that the NH2 minus, it has a very, very great affinity for protons, because the conjugate acid of sodium amide is ammonia with a pKa value around 36. So that is another way to produce methoxide. And then yet another way, a rather expensive way to do it, is with the Grignard reagent. And you can use a Grignard reagent that it has a great affinity, because the pKa value of the conjugate acid of CH3 minus is the conjugate acid is methane, And the pKa value of methane is around 55. So it's a huge number. So that is another way to produce the corresponding alkoxide and methane. Acidity of the phenols. Well, phenols are more acidic than regular alcohols. Why? Because when you have a regular alcohol, let's say you have CH3OH, if I donate a proton and I produce CH3O-, so then now, how many additional resonance structures can I write down for methoxide? None, right? And so we are stuck in having the negative charge on the oxygen. But if you have phenol, once I remove a proton from phenol, so if I donate a proton from phenol, then I can produce O-, and then I can bring the negative charge to the ring, and I can localize the negative charge here, or here, or there, right? There. And so I can write down 3 additional resonance structures for that phenoxide product. Now, we will get to discuss now the relative acidity of regular phenol. So here we have just regular phenol. So what are the resonance structures that I can write down here? Well, I can bring my pair of electrons here, localize there. So that will be 1 additional resonance structure. Or I can bring the negative charge here. Oops, sorry. There. Or I can bring even the negative charge there. And so there you have several additional resonance structures that we can write down for phenol. And that is the reason why the pKa value decrease. The pKa value is 989, so it's substantially lower than the pKa value of an alcohol. An alcohol is around 16. How about if we have a nitro group in position para, so in a relative position 1, 4, right? Para position. Well, there you can see that I can bring the negative charge here, here, and there. And there, the oxygen can help me to write down yet 1 more resonance structure, right? I can write down yet 1 more resonance structure. And that is the reason why the pKa value decreases even more. And we can see that the pKa value is 7.15. So it's even more acidic. The paranitro phenol is even more acidic than regular phenol. And then finally, how about if we have a methyl group in position para? So 1, 4. And so in position 4, we have a methyl group. Well, you may recall from chapter 6, chapter 7, we said that the alkyl groups are electron donors. And because of that, if I bring the negative charge all the way to the para position, that is not going to be so great, right? And so there, if I have a negative charge precisely where I have an electron donor, and so that will be a sort of a short circuit there. So that particular resonance structure will not be so good. And that is the reason why the pKa value increases with respect to regular phenol. Okay, so let's stop here and we continue later.